All right, welcome back everybody to our final week of this class. We will be doing chapter 16 today and then starting reviews later today. You'll notice on Friday, I sent out a kind of a summary of like high points. Again, this isn't the only thing, but this gives you a place to study. If you understand, like, for example, on the thing I sent, if you understand that these are all the rules or most of the rules for nomenclature that we've learned, then you should be able to, let's see, I'm pulling up the that review part 1 doc. So for example, on the review, for chapter 1, the hybridization, what does a double bond look like? What's the shape, right? That helps us determine a lot of things. And then I go into functional groups, and then I reintroduce functional groups again down in nomenclature. So it's kind of like you should see things happening again and again throughout that review. And so as those things, start, building, you'll know that those are important 1 time, 2 times, 3 times, etc. And then stereochemistry is added in with the basic rules of nomenclature. And that way we can also think about what our next section, which is prefix, infix, suffix, and then how that rolls into different classifications of things. And so I've gotten through chapter 11, just the IR spectroscopy, NMR spectroscopy, and the highlights of those. And then I'll continue with the remaining chapters today. I should have that up hopefully today so that you can start that for your study session. And then we'll of course do our studying starting today and tomorrow. Okay, so first thing is, yes, if you're missing, double check your grades, make sure that there's something there. There should be something there for everything but our last activity and our last homework and our last exam. There should be grades for everything else. If there isn't, go ahead and email me and I will give you an explanation, or we'll figure out something, okay? All right, for administration for this week, obviously here's our new Zoom code, and so thank you all for coming. We have homework for chapter 16 only. Go ahead. Somebody have a question? Oh, muted themselves. Okay. Chapter 16 is the only homework due this week. It's due on Wednesday at noon, and then after that you will be able to review. All of the other homeworks are now reviewable for the exam. So you should have plenty of opportunity to go back, see what you got right, and figure out what the right answer is. Okay. Our group project number 1, which we were supposed to do on first week, we're going to actually do on Wednesday to get that last 20 points applied to our grade. So we want to try to get that done as well. Your participation grade was by looking at the participant window and finding out if you've come at least 3 times a week and or have done homework and or have done other things. You'll get those participation. That's where participation points were added. So, and if you have an issue with that, go ahead and email me. The final exam will be on Top Hat from 2 p.m. to 4:30 p.m. That's not our regular scheduled class time, but it is when the university schedules finals to make sure that no finals are overlapping. So take note of that time on Thursday from 2 to 4:30. I will be, of course, monitoring live just like before. And once you are done with that, I believe there are 60 questions covering all 16 chapters, and it's scaled so the raw number is the one you'll see at the end of it. Don't worry, I still need to do my scaling on that to try to rack and stack and get all the grades. Overall, I think we've racked and stacked the grades pretty good so far on that last exam. A lot of you did pretty well on that last exam. So after the curve. So I'm getting the kind of how to do this online a little bit better. And so I think we'll see even better grades or less curved grade for the final. Okay. And obviously there will be no half-hour happy hour this week because we don't have a Friday. However, if you do want to email me or communicate, go ahead and I will be available for that. Okay. That is all the administration I have. Do you have any quick questions about the administration chapters or how we're going to do our review? Okay. Well, you're typing that into the chat or unmuting. I'm going to go ahead and share my screen so that we can start doing chapter 16. There we go. Chapter 16. We're going to do all 3 goals today. The key here on chapter 16 is to do with, let's go with that and this. Hang on, my chat went away. Let me get a chat screen up here again. There it is. All right. So the key thing about polymer chemistry is I want to introduce the topic of large molecules. And you'll see is the functional groups we used in the carboxylic acids and other chapters are one set of just repeated functional groups we'll see in one type of polymer chemistry. And then carbon-carbon bonds will be repeated again and again in the second type of polymer chemistry. So the key here is we have 2 general types of polymer chemistry, but the introduction here has to do with what a polymer is in morphology, okay? And the reason it ties into organic chemistry so well is we use a lot of organic chemistry to make the small molecules that you make big molecules out of. And then we have a new reaction that you haven't seen before in goal 3, which is using radicals to create polymers. And so it's a new way to create a carbon-carbon bond, and it has a weird kind of approach to it. So that's why we're gonna look at that in particular. So the first thing we need to think about when we think about polymers is basically some definition. So poly just means many, mono means one, okay? So polymer is a many molecules hooked together, and you make them out of monomers. So you make one unit, you add another unit to it, and now it's a dimer, and then you add a third one, and then it's a trimer. Just like we added different things to different groups to our nomenclature, we have mono, di, tri, tetra. Okay, after it gets so big that you don't want to really count it, you call it a polymer, just many mers. Okay, so that's the whole concept between a polymer, the difference between a polymer and a small molecule. Now, because of this, there's also some subclasses of polymers that we call. The first thing we want to do is define it as plastic, okay? Plastic is a generalized term for a polymer that can be molded when it's hot and then retains its shape when cold. So plastic bags are actually made by blowing, and you can also, your plastic bottles, the PET bottles, are also available to us through that molding process. And we call those the plastics. Specifically, we call them thermoplastics because you can blow them, you can, form them with heat, and then by heating again, you can reform it, and by heating again, you can reform it. So if you can do it time and time again, that's what we call a thermoplastic, thermo meaning heat. So you heat it, and then plastic kind of means rubbery, and so you can mold it. Now, in contrast, there are things like epoxies, which are what we call thermosets. Once you cook them, once you bake them, they will not remelt. They form a solid, and they never will dissolve or be remelted. So those are 2 different classes there. So a polymer is just a very large organic molecule. A monomer is what you build polymers out of. And a thermoplastic is something you can mold with heat again and again and again and again. Okay, so that being said, we have a way of noting these things, and my screen was not sharing there. All right, so we have a way of talking about these things. And so the way we talk about these things is we have that repeat unit, right? That monomer, right? The one you make all the other units out of, okay? So by the number of those things you have there, we call that the degree of polymerization, or basically the number of repeat units, okay? So in the case of this small molecule here, This is a very common molecule that we'll talk about in goal 3, and it is called propylene. So it's 3 carbons with a double bond. So propane, propylene, or propene. Okay. When we polymerize these, we repeat them again and again and again. And so we're adding units. And if we looked at it here, we could cut those units in those little different sections. So this is 1 unit, this is another unit, this is a 3rd unit, this is a 4th unit. Okay, so the number of units you have that are were from the same monomer or starting material, that's what we call your degree of polymerization. Okay, and to draw that, would be the monomer here, and if we were to draw the polymer, it'd be this really long structure here. Well, like you know, organic chemists like to do shorthand, and so in polymer chemistry, we do that same thing by showing just the unit that repeats, and then we put a bracket around it and say N for however many numbers of that repeat unit we have. Okay. So now we've gone from an individual unit, a single chemical compound, through what it would look like if we drew it out completely, to the shorthand where we only have to worry about the unit that repeats and how many of that unit we have. Okay. So to name polymers, what we usually do is take the small molecule that we made it from and add the word poly to the front of it, okay? So if we had a small compound, remember in our chapter with benzene and benzene derivatives, we named this compound styrene. So if you were to take this compound and turn it into a polymer, you would name it polystyrene, okay? And an engineering term for this compound here is called vinyl chloride. So we call that polyvinyl chloride. This is more commonly, you may have heard of it as PVC. It's used in plumbing pipes. That white pipe that is at Lowe's and Home Depot, that's usually polyvinyl chloride. So you take a very small molecule here and you turn it into very huge numbers of that unit together to make it into a polymer. Okay, so polymers don't just have to be straight in a long chain of individual units. There's a bunch of different things you can do, and this is only a few here. You can have a nice straight polymer, which things like polystyrene and the polyvinyl chloride, or PVC, typically look like that. But polyethylene, which we'll talk about in a little bit, actually is typically branched, and so we have different types like high density and low density available to us. But then if you're really precise about how you do things, you can change that morphology to be all sorts of structures. And what we'll see in things like cross-linked networks here, that's the polymer used in baby diapers that sucks up water. It starts out as a cross-linked polymer that swells when water gets absorbed in it, okay? And there's some actual drug therapies that use these little branched things where it holds molecules until they get into the stomach or the blood and they are released slowly. So there's a bunch of different things we can have with this, and they each have different properties, but we're not going to talk about that specifically. I just want you to know that it is very, very diverse and there's an entire field of chemistry associated with just polymer chemistry. Okay. So the other thing we have when we have polymers is because you have those long chains and you have chains that can be branched and things that come off, they tend to do what we call crystallize as they are cooled. What that means is that in your hydrocarbons, like in your alkanes like hexane, when it freezes, you have that van der Waals interaction holding that together. Well, in a polymer, you have that same kind of interactions happen. And so when they crystallize, they tend to have what we call crystalline domains. But we always have disordered or amorphous domains. What that means is that the polymers are so big and so complex that rarely can you make the entire thing all organized and all ordered. So most of the time you have some places that are ordered or have crystals in them, and then the rest of the polymer gives you those amorphous or rubbery zones. The cool thing is that by balancing the crystal domains and the amorphous domains, you get different properties from the same polymer. Okay, so for example, things that are polymers that are straight and have no branches and have no side chains have a higher degree of crystallinity because there's fewer imperfections. So that means more and more and longer parts of these can stack up. The other thing that helps is when you have things that can hydrogen bond, like amides or amines or alcohols on them. These strong intermolecular forces can increase the crystallinity of the materials and increase their structure and their properties right here. One of the other things that we need to think about is the more crystalline something is in a polymer, the more opaque it is, because those crystals cause scattering of light. So when you see a plastic that is white or opaque, that has a lot of crystalline domains in it. Things that are clear have smaller crystalline domains and a more amorphous structure, more non-crystalline areas. Okay? So, and when we have these polymers that have a lot of amorphous areas, because crystals cause scattering and crystals cause it to become less transparent, if they are more amorphous, they tend to be clearer, and therefore we call them glassy polymers because they look more like glass. You can see more through them. And so one thing you can look at is glassy polymers tend to also be a little more flexible, more rubbery in that state, because there's fewer crystals to inhibit that motion. Okay, and we defined this transition of going from a glassy polymer to a rubbery polymer as the glass transition temperature. It still stays transparent going from the glass state to the rubbery state, but it actually will change the properties going from more rigid polymer to something that's more flexible. And we use that to our advantage when we do that forming of a thermoplastic. The glassy state or the harder state is the state we want to have the polymer do the work we want, like be our bottle to hold our water. But we had to go through the rubbery state, heating it up to make it fill the mold that turned into that bottle. And then we cooled it down back into its rubbery state. So it's kind of interesting that you can take a polymer, get it till it's rubbery and liquidy, and then form it and then cool it down, and it'll hold that shape and do that work that you want it to do. Okay, so the big example we have for that is what we call PET, or if you look on your recycling number, it's actually PETE, which is polyethylene terephthalate ester, or in this case, polyethylene terephthalate. So the cool thing here is that if we looked at this part right here, we talked about this part of the molecule in our carboxylic acid domain. We called this terephthalic acid, okay? So it is a dicarboxylic acid of benzene, and we talked about, excuse me, allergies are giving me heck today. Then we also have this part right here, which is ethylene glycol, or the diol of ethylene, and that's the other part of the repeat unit. The cool thing is that when you add this together and make a polymer, it's going to look something like this right here. And it's got these groups that can have dipole-dipole interactions. And you can, by changing how you process this, it can be 100% clear or only transparent regimes, or you can actually start to crystallize it more and more and more. And that changes its color and it changes its durability. Okay, so when completely amorphous polyethylene is formed by cooling it very quickly, it gives you very transparent things like plastic bottles. So when they do this, they take a blank and they blow it into a mold and they cool that mold down very quickly. And that gives it that clear color, okay? If you take that and you cool it down more slowly, what happens is it becomes more crystalline. And so you can actually get fibers like Dacron, which is a fiber, a textile fiber that's very strong and tough, that can be used in fabrics and in tires. But you have to cool it down more slowly, and it has a greater number of crystalline regimes. Okay, so that's one of the cool things about polymer morphology, is that how crystalline it is can change its properties. It's not just the molecular weight or the hydrogen bonding that affects its properties. Like in smaller molecules, we have another tier of interactions that helps us control the durability, the strength, and the processing of these polymers. So the amount of crystalline area and non-crystalline area is that tool we use to our advantage. Okay, so in the case of low density polyethylene, which is a polyethylene, which is just, you know, that's ethylene right there. And so polyethylene just looks like this. It's just carbons and hydrogens. And this is the repeat unit here. Most low density polyethylene also has branches. And because of these branches, it can't crystallize very well, which means it's more likely to stay clear. Okay, so polyethylene bags are, you know, the kind you get at the grocery store right there. And they're actually made not as a sheet by itself, but it's made as a tube, because you can warm it up and then blow air into it. And then if you blow cold air on the outside, it solidifies. And then that rolls it up into a giant roll, and they can slit that or press it or do something else with it. So this is taking it, very interestingly enough, from, you take it from your area here, you melt it into its rubbery phase, and then you blow cold air onto it here, and then that takes it back into its glassy phase. And then if you do it correctly, it'll be transparent and clear with having very few crystalline regimes. Okay. In contrast, you can take high density polyethylene or even PET, polyethylene terephthalate, and do what we call blow molding, which is where you take a small empty tube of just any shape at all, and then you heat it up, and then you put it into a mold that is colder than the polymer you have, and you blow compressed air into it. So what the air pressure does is that blows the polymer to the outside mold. The mold immediately cools it and sucks away all that heat, and then you have your nice solid finished product out of there. And so this is a different way of processing things than any other way in chemistry. It's these two ways of using heat and air to change the shape of these polymers. Okay, and so here are some very common polymers and their recycling codes. The first one, of course, is PET, or PETE, which is polyethylene terephthalate. It's that carboxylic acid derivative and an ethyl alcohol derivative. And those are used in a lot of different things like fibers and bottles. Then we have high density polyethylene. That has fewer side branches. And with fewer side branches, it gets stronger and more crystalline. Therefore, it tends to be less clear than low density polyethylene. It is tougher and more opaque. The third kind here is what we call PVC, which is polyvinyl chloride. It's used a lot in insulation. Your credit cards are made out of it. It can also be used as plastic floor mats, right there. Another polyethylene that has a lot of side branches makes it a lot more flexible, so we can use it for trash bags or grocery bags. Polypropylene, which is, starts out as propylene. It tends to be clear when you cool it down very quickly. So it's actually used in the clamshell packaging that you have at stores and, that are so hard to get into with the scissors. That tends to be polypropylene. And so you can do those on multi-layers as well. Polystyrene, you may know polystyrene from your Solo cup or the styrofoam cup, both of which are used as a polystyrene system. And so, and then There's a whole bunch of other plastics that can be reused, but they are not listed here. Okay, so that is our goal 1, polymer definition and polymer morphology. Okay, so the key for polymers is they are large molecular weight materials. Okay, most of the molecular weights of the materials we do, maybe 1 or 200. Polymers can go to millions of molecular weight. One molecule would be, if you had a mole of one molecule of that polymer, would be 1,000,000 grams per mole. Okay, so that's the big definition there. The most useful polymers you're looking at here are polymers that can be thermoformed. And when they thermoform, they go from a rubbery state where they can be blown and twisted and pushed into molds to a glassy state where it'll be hard and rigid, and you can use it for your plastic bottles or your pipe or your fibers. Okay. All right, questions on goal number 1, polymer morphology. I think I unmuted everybody. Okay, you're unmuted. Okay, so what I'd like to do now is go to what we call step growth polymers. Now, there's 2 types of polymers, and they're step growth polymers. And step growth polymers look like regular organic chemistry reactions we've done so far. Making an ester, making an amide, making an ether. These are things that we call step growth polymers because you do one functional group at a time, and add them together and together. Okay, so the more common ones of these, you'll see that the names are based on the functional group made during the reaction. So if we look at how we have what we call amides. When we have a carboxylic acid and amine react, we have an amide. When we have a carboxylic acid and an alcohol react, we have a polyester. We have a special kind of carboxylic acid derivative here called a polycarbonate. Polyurethanes are also a carboxylic acid derivative, and we'll talk about that. And then epoxies. Epoxies are those cyclic ethers, those 3-ring cyclic ethers we talked about in the alcohols and ethers chapter. Okay, and we're going to look at all of those and why those different polymer types are called based on that functional group. Okay, so the first thing about polyamides is that we take a carboxylic acid and an amine and react them together to create a polyamide, right? That's how we made amides to begin with. The only difference here is instead of just reacting one side to one side, we actually end up reacting it on both sides of a molecule, okay? So if we were to just take this part of the reaction to happen, we would create an amide, right? But you have a carboxylic acid on this side of the chain and you have an amine on this side of the chain. So that means this can react with a carboxylic acid and this can react with amine. And it keeps stepping up the molecular weight. Every time you add a unit, you've stepped up the molecular weight. That's why it's step growth polymerization, okay? So in the case of making nylon, which is a polyamide here, we typically do it by first making what we call the nylon salt. Remember, anytime a carboxylic acid comes in the presence of a base, it forms a salt first, right? Then with heat and pressure, we can eliminate water and we end up making the polyamide. Now, notice that we have a nitrogen with a hydrogen bond double group, and we have a carbonyl, and the hydrogen can bond to that oxygen. In fact, that's what happens is it gives us what we have is we have little teeny hydrogen bonds all the way down the polymer chain, okay? So now, because the polymers aren't just going to, lay out flat, because the polymers aren't just going to go straight without a reason, what you do is you actually take the chains and you pull them. And this is called drawing out or cold draw. And when you pull them, that stretches all the single bonds out to their max length without breaking anything. When you do that, the hydrogen bonding groups start to align. The more hydrogen bonds you get, the more crystallinity you get, the more tensile strength you get, and the stiffer the polymer becomes, okay? So the polymer itself, when it's amorphous, can actually be quite rubbery, but by pulling it and drawing it out as a fiber or a film, it becomes much more crystalline and stronger and tougher. Okay. So the one we showed here is what we call nylon 6,6. And the reason it's called nylon 6,6 is if you look at this, we're using hexadioic acid. So there's 6 carbons in this change, and we're using hexane diamine, 1, 2, 3, 4, 6 more carbons, right? So you get 6 from the carboxylic acid form and 6 from the diamine, such that you have nylon 6,6. Okay, and so you don't need to know this reaction. I just want to show you that the way they actually make nylon, the carboxylic acid is from benzene. They reduce it down to cyclohexane, then they oxidize it, and then once you have this cyclohexanol right here, you can use the eno keto tautomerization to allow you to break the ring and make this 6-membered dicarboxylic acid. Okay, so to make the amine portion of this, we get to use what we call one of the reactions that we can use to make primary amines is we'll make an amide first by making the salt of the carboxylic acid. Notice there's 6 carbons in the chain here. They'll make the salt, and then by removing water, we'll get to this amide functionality. And then by reducing down the carbonyl on both sides here, we'll get to the 6-carbon chain with the nitrogens at the end. So the cool thing is that we're making both halves of the monomer, or both halves of the polymer, from the same material. Both are made from benzene. Okay. So in contrast, if nylon 6,6 was taking a 6-membered amine and a 6-carbon chain carboxylic acid, nylon 6, we are taking a compound that has the carboxylic acid and the amine on the same compound. And the way we have that is doing what we have the cyclic amide. When we remember, we called the cyclic amides lactams. Okay, so in this case here, if you count the carbonyl, we have a total of 6 carbons in this lactam to make a 7-membered ring. And you remember that 7-membered rings aren't that stable. So all we have to do is a little bit of heat and a little catalyst, and it ring opens up to that long chain polymer. And then if we stretch that polymer out, it again has those places where we can get hydrogen bonding all the way along the chain. Okay. Another type of polyamide is actually can be made with benzene derivatives instead of those flexible carbon saturated carbon chains. And when we do that, we call them aromatic amides, or aramids is the short name. And what we have right here is because we now have lost the flexibility of our 6 carbon chains here, these things become very, very strong. They're very rigid, they're very tough, and they hydrogen bond very strongly with the groups along the chain right here. And so this is a polymer that's a polyamide because that's the functionality, but it's completely aromatic. And they are used in bulletproof vests, bulletproof jackets, and in fiber reinforcing of things like, you can even fiber reinforce tires with these things. They're so strong. Okay, so let's move on from the polyamides to the polyesters. We've already introduced polyethylene terephthalate, which is an aromatic dicarboxylic acid we learned about in the benzene chapter, and then ethane diol, or sometimes called ethylene glycol, right here. We typically make this through a transesterification reaction. So we learned about the Fischer transesterification reaction in our carboxylic acids derivative here. And we learned that by having a little bit of acid catalyst, we can exchange one alcohol for another alcohol. And in this case, we're exchanging this very high boiling, this boils around 200 degrees C, alcohol with a small alcohol, this methanol, which boils at 56 degrees C. So we drive the reaction by exchanging one alcohol for the other alcohol to make the polymer chain, and then we eliminate this as a gas coming out of the reaction. Okay, so this is the Fischer transesterification we used in the carboxylic acids derivative chapter. But again, it makes that very tough material. And if it's low crystallinity, it's nice and transparent. If it's high crystallinity, it's tough and opaque. Okay, so how do you make ethylene glycol? Well, the way we make ethylene glycol is we typically take ethylene and turn it into an epoxy right here. And then we learned that we can attack an epoxy with any nucleophile and it will open the ring up. In the case of this, if we attack it with water, we'll end up getting an OH on either side to give us our ethylene glycol. Terephthalic acid is made from a benzene derivative we call xylene. And if the two methyl groups are opposite each other, it's the para version or the 1,4-dimethylbenzene. And we can oxidize just the ends here to give us carboxylic acid derivatives. And that will get us to our two starting materials. Okay. Now, the next polymer is what we call a polycarbonate. It's kind of like a carboxylic acid ester, except instead of having the carbonyl bonded to a carbon, the carbonyl is bonded to another oxygen. And so if we look at just our functional group right here, the first half of it here, if we cover up that half, it looks like an ester right there. But because we have an oxygen on the other side, it is now our new functional group. So we have an oxygen, carbonyl, and then another oxygen here. That brings us what we call a carbonate. It's a derivative of a carboxylic acid. Okay. So in the old days, we used to take a compound called bisphenol A, which can be made into the salt like this. And then we added a gas called phosgene. Now, phosgene is the diacid chloride of carbonic acid. So it's just another carboxylic acid derivative. It's an acid chloride derivative of it. And we use that to make this polymer here. The cool thing about polycarbonate is it's incredibly transparent, very low crystallinity, and it's a very tough material. It's part of what is used in bulletproof glass. It's also the major thing used in safety glasses. It's very tough, very resistant to impact, and therefore we use it in safety glasses as well as the plastic shields we're seeing around town for that are in front of cashiers and stuff. Those are also most likely Lexan or polycarbonate. Okay, so it's a very tough, transparent polymer. It can also be used in snowmobile helmets. It can be used in football helmets, all sorts of stuff. Again, if you don't put fillers in them or you don't put color in them, it's nice and transparent and can be what we call unbreakable windows. It's not bulletproof windows. That's something else. You have to have multiple layers for that, but it does make what we can call them unbreakable windows. All right, so the next derivative I want to talk about is what we call a polyurethane. And in the case of a polyurethane, what we're doing is it's kind of like a polyamide and a polyester, but it's all in one functional group. So let's just look at the functional group here. So we have a nitrogen bonded to a carbonyl on one side of it and an oxygen bonded to the carbonyl on the other side. So it's the perfect mixture of an amide and an ester. And so it's not either, so we have a new name for it. We call it a urethane. Now the coolest thing about this is we actually make this through an unusual polymerization where we're taking an alcohol And the alcohol is acting as a nucleophile and attacking the carbonyl carbon to make the chain. Okay, so the polyurethanes can be used to make foam. If you make it one way, it'll be a polyurethane foam. If you make it another way as a long molecule, you can actually make very stretchy fibers out of it. Things like spandex and lycra are used by making fibers out of this unit. The reason you can make these nice elastic fibers is you have a rubbery section in this small section here, and you have a hydrogen bonding section in the urethane. Okay. The last thing I want to talk about is the only thermoset we'll have here, which is what we call an epoxy. Basically, epoxies have at least 2 epoxy groups on the chain. Once they react, you cannot redissolve them, you cannot melt them, okay? So that's why this polymer is different than all the previous polymers in this section. All the previous polymers in this section can be melted and processed after you make them. This cannot. Okay, so why can't we do that? Well, the reason has to do with how we make the epoxy, and specifically the fact that it's a dye epoxy. Okay, so going back to what we used for polycarbonate, we're going to use that bisphenol A again, and then we're going to add a chlorine derivative of our epoxy here, and we're going to make it so we have an epoxy at 2 different ends. Now, remember, when we had an epoxy, we could attack it with a nucleophile, and that nucleophile would open the ring and give us an alcohol and the functional group that we just attacked it with. So that's what we see when we do these reactions. We typically react the diapoxy with an amine. Okay, if you have a 2-part epoxy in a tube and you push the syringe out, one part's very viscous, the other part is smelly and stinky. The smelly and stinky part of that is the amine part there. It's typically a diamine or a triamine. And what it'll do is it'll attack and ring open and give us this functional section here. Notice the cool thing about this functional section here is that alcohol itself can act as a nucleophile. The amine can still act as a nucleophile, and there's lots of hydrogen bonding. So you never just get a linear chain, you always get multiple reactions with multiple side chains. That's why we call it a thermoset, because it cures once and then you never have to worry about it again. Okay, so those are the step growth polymers. We start with a monomer, we add 1 unit to it, and it grows and grows and grows and grows in that alternating monomer unit, monomer unit, monomer unit. Any questions on that? Okay. All right, well, that brings us to chapter 16, goal 2, and we're right at the 12:40 mark. So what I would like to do is I'd like to stop recording and then answer any questions you have before coming back in our next section.